Hi, my name is Sean Thomason, and this is my presentation on artificial blood vessels. Sorry, I'm trying to get to the next slide. So artificial blood vessels are incredibly valuable medical devices. They're typically used to repair ruptured vessel segments. If there's a ruptured vessel segment, then that can lead to internal bleeding and the eventual death and or dramatic decrease in life expectancy or life quality for a patient. They can be assisted in restoring blood flow if there is a blocked or congested or not quite ruptured but malfunctioning vessel. Then the artificial blood vessel can be used to either graft that or to replace it entirely and enable that blood flow to continue to go. And they are also used for grafts onto malfunctioning vessel segments so that they can repair any slight lacerations or cuts that may be impeding their efficacy. So, needs of patients typically come down into three primary sizes, or at least for the purpose of this experiment, we looked at three different sizes. For 1 millimeter lengths, those are typically used for grafts. It would be for an individual segment, or if there's a minute portion of the vessel that needs to be repaired, that would be the primary consideration. There's a high potential for billing, given that the procedures that are associated with these very fine-tuned procedures would be much more expensive, and so we would be able to, I guess, upcharge on that. But the downside of that would be the low usage rate associated with, with that, minimal use, or I guess the lack of procedures that would be done. Secondarily, we have 10 millimeter lengths, which are used to correct ruptured or malfunctioning segments. They can either be grafted on, or they can repair, or they can replace, very small segments of the vessel itself. Typically, the ruptures themselves are longer than 1 millimeter, but far less than 100, which puts the 10 or multiple segments of 10 in the ideal range. And given the applicability of the 10 millimeters, they would be able to be used at a higher usage rate, but that would also bring down the billing. But at the end of the day, it would even out given the more procedures that would be done with them. Finally, we have the 100-meter lengths, which are used to replace segments of vessels with improper blood flow, because given that that's a much longer segment, you could potentially cut them up, but then that could reduce the efficacy of the actual segment itself. So they're only used for long stretches where there is decreased blood flow, something's malfunctioning, and not really ruptures, because you don't get ruptures at that length. There's a high potential for billing, very similarly to the 1 millimeter, given that the procedures themselves would be quite intensive, but also because the procedures are so intensive, there are less of them, so there's a low usage rate. So the materials that we're considering for the present experiment are polycarbonate urethane. It is actually that picture right there. It is used widely throughout the medical device industry, primarily in grafts, because they're able to have a low ion release. They are biocompatible, so they are encased. Once they're inserted, they're not attacked by the body, as well as their low cost point, which is typically around $3 per kilogram. Secondarily, we have polyglycolic acid, which is a medical industry staple. Its highly crystalline structure allows it to integrate easily within the body. It doesn't have any natural or, impeding ion release, and it just works with industry compliance. There's a large amount of research associated with it. So if you're looking for a name brand, then you would have to go with PGA. But associated with that, given that it is so widely used, the price is very high. It is $108 per gram of polyglycolic acid. That's usually in the powder form, and you can make more after the fact. Finally, you have the polytetrafluoroethylene. That's a long word. It's typically used in heart valves and stents and grafts. It's very similar to polycarbonate urethane. It just has a more crystalline structure, making it easier to work with. But it's much less used in the industry. It is primarily used for very niche stents or grafts for the body. So in this experiment, we tested the 3 different materials that we just talked about, as well as the 3 different lengths that we just talked about for their adherence to the inlet volume flow. We wanted to see what would be able to maintain the overall pressure level that is coming in, or I guess the natural pressure level that is within the body, which for this experiment we used 70 millimeters of mercury as our inlet. And we also considered cost as an important factor in the material selection, given that we are trying to produce this and put it onto the market. The models that were utilized are shown on the right. The top model is the 100 millimeter, the bottom right model is the 10 millimeter, and the left model is a 1 millimeter. So the results of the 1 millimeter for the polyglycolic acid and the PTF, I'm just going to start using the acronyms, they had an average of 0.02 pressure rise when the volume inlet and the inlet volume flow came in, while the polycarbonate urethane only had a deviation from the original inlet increase of 0.01 pascals. Now, the overall small, or I guess the minuteness of these changes is due to the low flow, but that's what's necessarily going to happen in the body. You're not going to see large pressure changes unless something is distinctly wrong. Secondarily, we have the 10 millimeter. The performance of the polycarbonate urethane was incredible. It only had a deviation, again, of 0.01 pascals, while the PTF and the polyglycolic acid had a much wider range of pressure changes that were happening within the tubules during the experiment, as well as they had higher deviation ranges of 0.02 pascals for both situations. So in both of these cases, the polycarbonate urethane has had lower deviations from the initial pressure and also been able to operate with less deviation, or I guess less ranges of pressure changes throughout that length. Now, for the 100 millimeter, it was more than likely due to the overall length, but the performance of every single material, every single model was the exact same. It was probably because it just kind of attenuated any pressure differences that naturally built up, and any differences that could potentially be seen were attenuated just given the sheer size compared to the other 2 models. So there was no real best pick for here. But of these, if we go back to the 10 millimeter, we're able to see in combination with, well, we'll get to that. For the data analysis, the polycarbonate urethane had the lowest deviation pressure range due to the inlet volume flow. So in both of the cases, the 1 millimeter and the 10 millimeter, those are the 2 that we're considering, it only had a deviation of 0.01 pascals after the volume inlet flow came in. And the low volume flow rate made getting distinct readings difficult to receive, but that's only going to be natural given how the body works. And if there is a distinct drop in pressure, that's typically a medical issue comprised of somewhere else in the body that's not directly associated with that area. And then finally, of those tested, the ranges in the pressure gradient shown in the 10 millimeter model were the most ideal, especially for polycarbonate urethane. It only had those 3 distinct bands, and that meant that of the 0.01 pascal change, it was all happening very smoothly, very gradually, and there's no real fluctuation throughout like you saw in the other 2 models. So for the conclusion and recommendation, the conclusion would be that the 10 millimeter length model is ideal in conjunction with the polycarbonate urethane. The 10 millimeter length is ideal outside of its performance in the experiment because of its overall marketability. It has a wide usage rate that we'd be able to market and potentially bring in more income from. Manufacturing the polycarbonate urethane is very easy to produce, very easy to mass produce, and it performs very similarly to any like the polyglycolic acid when it's in its resin form. So overall, it would be very similar to what the industry is already accustomed to, and it would not be bad. And profit again would be there. And finally, polycarbonate urethane is ideal just because it has the lowest deviation and it's the lowest cost material. So with its performance in the experiment, as well as its overall low cost, it is the best choice that we have. Thank you.